my name is Martin Servin. So I have two legs, one in industry and one in academia. I'm a co-founder and scientist at Algorix. At Algorix, we develop physics engine, high fidelity physics engine used in many industries and academia for heavy equipment and off-road vehicles. We're 35 people. One of us, Urban Wikman, is present there in the room today. And then also on my university side, I lead a research group in digital physics, where we're interested in pushing physics simulation forward and combining it with artificial intelligence so that we can create control and planning of these machines that are more intelligent and informed about the physics. So the title of my talk is Visions and Technology for Physics-Informed Heavy Construction Equipment. So, and let's begin with some of the visions. And let's first think about the drivers for automation in these industries. It's not autonomous vehicles that are the primary goal. Besides productivity, sustainability, and labor shortages are really strong driving forces. Construction industry is a heavy user of energy and CO2 emissions, and safety is obviously an issue in these scenarios. In some parts of the world, labor shortage is dramatic. In Japan, for example, 1.3 million fewer workers are present over a 10-year cycle. So there's a need to really fill that gap with technology. So that's really driving a lot of the work. And there are some trends. I don't think I have to push for artificial intelligence, but I want to direct to what's going on in space right now, in the space industry, and particularly the Artemis program. So we are seriously going to build a base on the moon, and there are needs for new construction equipment, heavily robotized for this, and many equipment manufacturers are now looking into how to redesign the machines and how to make robots out of them. Here you see example from Komatsu's work thinking about this, and we are involved in some of the simulations here. So some expectations on how this is playing out now in the near time. I think digital twins will be increasing a lot in use. It's already present. We see work sites continuously being scanned with the drones to have an update view of the status of the construction sites. And also each machine is also very much of a sensor to this connected system. When we have a machine operating in one place in the work site, when you monitor the dig forces and energy consumption, it tells a lot about the soil properties and the information about the rocks in that place. And that information, we will see that being shared in real time with the system, and thus with other vehicles that can react to that in the planning and control. Having a digital twin of the mine update to the current situation, that can also be used in a good way in safety assertion. Simulators are used heavily today to test new autonomous systems before you deploy them, but I expect that we will see continuous safety assertion using simulations continuously. When you make an update of the automation system, or when the work site has changed in layout somehow, simulations iterating over many scenarios will probe for safety concerns or risks or things that you haven't thought about or trained your models for reacting in this behavior. Having this digital twin technology, you want to also apply it to long horizon optimization. This is rather mature already in mine sites where they simulate all continuously the workflow and how the material flow and how the machines should be positioned in real time to work as a collaborative system with high energy efficiency and productivity. Clearly more difficult in a construction site that is changing more rapidly and much more heterogeneous. We will see this down on machine level also, that we will build in each machine a local simulator carrying possibilities to represent the environment around the machine, both the physics of the machine and the environment. We will see tiny physics engines that can be used in planning and control that has computational properties of the rocks that the machine is handling. So technology side at Algorix, we are clearly building technology to make this possible. Here's an overview of the tool chain that we offer with the parts model, simulation, and then environments for testing and learning and training your solutions. At the model side, well, your vehicle models, they typically come from CAD. There's a pre-processing state to make them simulatable, to assign physics properties and couple them to drive lines, etc. The environment typically come from LiDAR scans or BIM models, and we provide databases of different types of soil libraries. All of this is then interconnected and mapped to your physics engine, in this case AGX. The mapping is done by connecting all of these 3D models with the physics using USD or BRIC that has a richer physics mapping. And then the scenarios, for instance, using open scenario file standards for that. That automatically maps you to the physics in the engine so that you can bring these work sites to life. You can also work entirely directly with the physics engine, either which is a C++ library. You can work directly on the core level, or you can work on modeling on high level components to combine drivetrain, tire models, terrain models into machines and work sites. There are many interconnections so that you can couple these to ROS or Simulink or different type of control systems, or you can move over entirely to work in Unity and Unreal, so that you can build really complex scenarios with high-end graphics. One advantage of the graphics capabilities in these engines is that you can easily produce highly realistic synthetic sensor data, video streams or depth images, LiDAR scans, to complement your time series data from forces and motion sensors on your vehicles. And there are many interfaces now to pipe that data into your environment, where you do analysis, data analysis, machine learning to train models or test controllers and feeding that back directly to the simulators. With AGX, you find a number of ready-made test scenes or tutorials that you can work on. For instance, reinforcement learning training of excavators, wheel loaders. And here's an example of the fidelity that you can achieve with AGX in the Unreal Engine. Nearly photorealistic camera streams, but not only good graphics, also thanks to AGX, there is high-end physics for the wheel loader, mechanics for the drivetrain, and the soil around it. One of the key features with AGX is that we have a so-called hybrid direct iterative solver, so that you can simulate the vehicle mechanics and driveline using a direct solver, and have a strong coupling all the way from the engine driveline through the scooping mechanism into the granular material that is then solved using the scalable iterative solver, so that you can do this in real time, but highly accurate and stable. Working with soil, you have the challenge that there are many types of soils, and working with a model like particle-based model like discrete elements, you have lots of parameters to tune to make them replicate real soils. To make that easy, we have ready-made library of different soils where we have. Yeah, so what you see in the image here, all these dots that has hundreds different soils that has been pre-calibrated for the micro model parameters to standard bulk mechanical properties like friction angle and the bulk cohesion, so that you can select like gravel, sand, dirt for your different scenarios. And making that choice has an important effect. Here you see a number of different soils, and they have dramatically different flow behavior and causes very different reaction forces on the bulldozing blade here, pushing them. Discrete element simulation, this particle simulation of soil, is typically not running in real time. To achieve real time, we have devised this multi-scale model where we basically, let me go back. We basically predict using we have made many simulations in advance and created models where we can predict where the soil will shear when you interact with it, and then we resolve only that part of the terrain and couple back to the vehicle using an aggregate model. So we are running two simulations in parallel and can advance the vehicle model with real time, but with high precision. And with that, we gain 1,000 times in speed up compared to the high resolution model, but losing only 10 to 15% in 10 to 25% in accuracy. So here is the example of what you can achieve with bulldozing in nearly infinite terrains. And you see the wavy pattern from the oscillations of the blade, thanks to the dynamics. This is what you want to control in the bulldozing simulation. With the wheel loaders, you get realistic reaction forces, and with a wheel loader, we are realistic driveline, and that's important to be able to do energy computations of what it costs, and also safety. So this is actually realistic behavior when you're applying a too large force on the wheel loader and the terrain is strong enough to withstand that. We have done many careful validation tests. Here we see example with data from Komatsu field test, where we run the real wheel loader carrying out many different loading cycles. Here you see 3 different examples. And then we make the corresponding simulations with the real-time model and the high fidelity simulation model. And we get an agreement down to 15-20% in accuracy on the forces in the hydraulic cylinders and the trajectory, and also in the resulting mass in bucket and the energy consumption in the machine. This can be used in many ways, and on Algorix you find paper collections on how it's used by different users, both in industry and academia. It's very much about earth-moving equipment, and here down you see also example of safety applications, how to design these crash burns when you have an autonomous vehicle losing control. How should you design them to really stop a runaway truck? I mentioned this example that we carried out with Epiroc, who manufactures these machines. It's a reinforcement learning control of this type of underground wheel loader. So it's trained to react on camera data, RGB and depth camera data, and point laser scans to avoid running into the wall and choosing where to attack this pile of blasted material and how to do the scooping. So this solution, it has 2 agents, one mucking position agent, that is where to attack in the pile, and then one mucking agent, which is how to control the linkage mechanisms for lifting and tilting the bucket and thrusting forward with with the wheels without spinning and spending too much energy and filling the bucket time efficiently. The next step in this work is to move from homogeneous soil, as was used here, to heterogeneous soils, where you have big rocks and boulders embedded into the rock pile. That's the really hard problem. So here you see we're going from 3D point cloud of a rock pile, extracting the large boulders that should be simulated as rigid bodies, and embedding them into the terrain where the finer soil is represented by this real-time terrain model. And then we can use that to train the models how to react to the presence of big boulders, how to move the buckets around them and into the buckets, and move them efficiently to the truck. Once you have this technology, you also want to move further to the more of the long horizon optimization problem. When you have a really big pile that you should dig and remove using a wheel loader and dump trucks that comes in shuttle. So the question is here, where in this big pile should you choose to attack? What's the attack point, what attack angle, and what loading motion, what digging control actions to choose? And this is a quite complicated problem. It's a really long sequence of actions that you have to take, both for a single loading, but also then repeated loading cycles. And each time you dig into the pile, you change the state of the pile. And if you do a local greedy search, you might turn the pile into a worse and worse state, so that future loadings becomes very inefficient. So you really have to optimize over a very long cycle. And using simulation for that, physics-based simulation will be way too efficient. So our approach to doing that is to, from the simulation, learn a dig predictor model that can run many times faster than real time and be differentiable. So we run many simulations and learn, depending on where and how we attack and what loading action we apply, what will be the loading outcome, how much mass, given a set of actions, what mass and what time and what energy consumption will it take. And it seems like a variational autoencoder regressor can do this problem well, predicting the mass working time, and also predict, given the input local height map where we dig into, how we will transform it into a new state, learned by these more high fidelity simulations. And it works quite well, at least if we give it up to 5,000 training data, 5,000 loading cycles data to learn from it. It can learn this pretty good, down to 5–10% in accuracy in these variables, which is slightly less than the accuracy we had in the field test validation studies that I presented before. So it actually seems tractable to do this. So to conclude, one should remember that energy use and safety is a major concern in construction energy when we're speaking of these big machines. So physics-informed models will be important for doing perception planning and control on these, because forces and energy are central in handling them. We are looking into how to make these simulation models embedded in the controllers and also turn this into differentiable physics. We are at very early stages and lots of research to be done there. And we'd love to collaborate on moving this forward, and also we hire. So please, you're very welcome to ask questions and interact with Urban Beekman, who's present in the room after this talk. So thank you.
Thank you very much. We have time for a few questions from the room.
Thank you, Martin, for your presentation. Any hint about the requirements for the hardware to execute your simulation?
So this simulation, the solver, it's CPU based. So it's I mean, ordinary or powerful ordinary workstation with good CPU performance and good memory. GPU for the visualization part, but we don't use dedicated GPU for the computing. And of course, you can shoot it off in batch simulation on a cluster, but with a similar type of CPU and memory performance as your powerful workstation.
Hi, thank you for the talk. I have a question about the sim-to-real gap. So how did you decide which sensors should you mount on the real vehicles in order to solve the perception and also the dynamic sim-to-real gap? And how do you collect the data? How do you transport it? How do you keep it? These kind of
So you mean in this scenario, on this comparison? So here the sensors were the force sensors in the hydraulic mechanism, and then we did tracking of the motion of the vehicle so that we could using the all joint encoders actually track the tip of the bucket also when moving inside the pile, and then some accelerometers on the machine. In this case, we didn't have available to track the surface of the pile.
My question is about the performance as well. So is this simulation in real time on the kind of hardware that you mentioned, like kind of a normal CPU with enough memory? And I have a second question. A lot of roboticists use URDF representations, which aren't really that useful for these kinds of machines with close chain linkages, etc. Is this simulator compatible with like SDF representation, and what should the community use?
Yes, so the simulator in the bottom here, bottom left, it runs on real time, and then you don't. It's a very not very computationally intense, so that will run in real time on a laptop. The middle one with a highly resolved particle model, it will not run on real time, even if you have a very powerful workstation. It will take a couple of hours to simulate. About data formats. That's one of the purpose of this new format called BRIC, is to be this type of extension to URDF to handle representations of more complex vehicles and not only the robots that doesn't have close links. So it's adapted precisely for that purpose. And it is a superset of USD and URDF.
So in terms of sensor simulation, do you support LiDAR or other modality of sensors besides the camera?
Yeah, so you can both access a number of sensor solutions through what's available through Unity and Unreal, and we have rather simple versions of sensors, both LiDAR and depth camera in the standard AJAX library, and work is ongoing to take them further as well with higher availability, because the sensor packages in Unity, for instance, is still not there as we would like. So we will do our own effort on that also.
Hi, thank you for the talk. Is this simulation could be used for evaluate the drivability of EV machinery, for example, sand of the vehicles?
Didn't fully understand the question. It broke up there, but so it sounded like you asked about evaluated drivability of a certain vehicle in sand. So the terrain. Sorry, wrong way. The terrain model, it reacts both to earth-moving tools that disturbs soil and simple versions of deformation from tires and tracks. So you can do it at some level. We know in the current terrain deformation model, it has some limitations on sharing behavior. So we're working to improve that, but you can also do it on the DM model level for sure.